Well, it's time to start, so I'm going to get going here. So, in the earlier talk about green energy, he suggested that he was using a partial model of Sweden, and I thought that was interesting. So, how do you rapidly model all of Sweden? Using the tools and libraries that I'll cover today is really what I want to get to. So I'm Glen Halley, electric distribution system planner and substation design engineer at City Utilities in Springfield, Missouri. Until recently, I was a modeler as opposed to a model creator. I usually don't have time to create models, which is why I've been working to translate models. Professor Manfredi, Dr. Castro, and others maintain OpenIPSL, a power systems modeling library for Modelica. I started working with Mathematica in college in 1990, plotting antenna patterns. I see system modeler and Mathematica combination as a good for all aspects of electric distribution and analysis. Among other things, Mathematica is a scripting language that is very necessary for translating. I began working on tools that will convert SIM to Modelica for OpenIPSL about 3 years ago. Professor Manfredi and Allset Labs have provided the library, the files to translate, and the verification. So who am I trying to impress with electric distribution analysis? Our customers. City Utilities is a municipal utility with 120,000 residential and commercial and industrial meters. We operate gas, water, electric, broadband, and transit businesses. Why does City Utilities need better analysis? We've seen challenges that we've not seen in the recent past, including an expected increase in demand of 40 to 50% by 2050, blackouts in Springfield during 2021 Texas winter storm, trade-offs between use of natural gas systems for residential heating or running our power plants, aging infrastructure, including a median transformer age of 47 years. How can system modeler and Mathematica be used to advantage? So create strategies that bolster resilience, redundancy, and capacity. I've focused on distribution load analysis and switching plans for several years. The addition of OpenIPSL could be a way to reach my goal. So today I'll cover our motivation, show a short demonstration, provide a little background into how the models were validated and verified, and I welcome any questions anytime during the session. So there are items in my presentation that are relevant to the use of system modeler and Mathematica, but I don't have time to cover them all, so I've included them in the slide deck. I feel like the most important part of this conversation is the proof of concept that shows OpenIPSL is a good tool and that the translations will make it easier to model or do engineering models. I just want to point out that PSSE is Siemens product that we use commonly for transmission systems. I don't personally use it, but it's what I've translated, and I do and am interested in transmission and distribution put together, which is something that I don't believe that tool can do. So why is translating data so important to me? It's a shortcut. I'll give you two examples. If I'm purchasing a transformer, I give vendors a few parameters and then reference IEEE 57, in which a transformer model is described. I'm saving the time of describing the model myself. A year later, a transformer will be delivered. I would spend an additional 6 months creating a specification if I didn't have the C57. My wife is a civil engineer and regularly starts her projects after she receives a survey as an AutoCAD file. The translation of the survey into a usable surface takes place when loaded into Civil 3D and saves the time of manually creating a surface. BIM communicates between Autodesk's various tools and can democratize access. Translation is synonymous with model communication. When the translation isn't possible, information that's necessary to make good decisions isn't available. For example, utility providers' transmission group planning group cannot model the distribution system in the PSSE file, which is the only available software to communicate with the Southwest Power Pool, which is our real-time operator. The inability to translate the model can result in a wasteful over-design. We're going to design it right, but it's going to be too much. SIM is information exchange. Simple model creation using SIM can solve the problem. So what does it take to move from using a translated model to understanding this particular model? I started with Power System Dynamics, a book. It's listed on the last slide, which describes many of the models in OpenIPSL. In this example, I've shown the two-winding transformer. Notebooks could be ideal for understanding the translation of no-load data and load data, or no-load losses and load losses into the transformer model. That's described in the C57, incidentally. The interface between Wolfram language and system modeler also automate this translation. So I've eliminated steps in my demonstration. We're going to move on to the demonstration. This slide is complete. Everything works with the version numbers shown, 13.2, which is not out yet. But I would recommend validating the model without modification if you get this up and running. And you'll see several notices in the updated. The notices are because we're still updating OpenIPSL. So, but they don't affect the result. So each bus contains the voltage magnitude, V, and angle, and also the current magnitude and angle. These are convenient quantities to plot, and I'll show you those later on. There are also several things to note about using per unit versus actual voltages, and that's really important to this particular model. So the other thing to note, I'm just going to kind of go over a little bit of the code. I work more with the Modelica code than I do with the graphical interface, but you can use the interface as well in this case, because I created the graphical interface just specifically so you guys could use it. So the PW pin connectors across variable voltage and flow variable current are stored as per unit. I already said that. And an example of the connector's use is in the pi equivalent transmission line out of the Power System Dynamics book that I mentioned earlier. This is so in this case, the line has a source end and a receiving end. And you'll notice that the real and imaginary parts of the PW pin connector are changed to complex variables in and that's so that when you look at the equations, they're easier to understand. If you're an electrical engineer, a KCL in that case. So one other thing to note about the model itself. So right now, I would recommend staying within the test cases, not using the examples, except for the example that I'm providing that you can download. And use the slide deck to show you how to do that. So I want to also point out that electric is the main source of most of the components. So in this demonstration, what I'm going to do, so we've got a transmission system model. It's the IEEE 14. And we're going to extend it with a distribution circuit, and then I'll show you the results. And I've run most of the simulation prior because it takes a few minutes to run it right now. We're going to try to improve that. So let's see if we can do this. Stop sharing. System. All right, so right off the start, I'll show you, this is a generator. And the generator is essentially broken into several major parts. I'm going to see if I can zoom in here for a second. We've got the exciter, and I'm sorry about this. The exciter controls reactive power using the field of the generator itself. And then you've got the actual synchronous machine. And then you've got the governor right here, which controls the speed of the engine and essentially decides how much load it's picking up. And then you've got the power system stabilizer, which is essentially a dampener, right? So that is the first thing to know is these are complicated models, and they've gone through the trouble to create all of them, including dams, like high water-based dams, and that type of thing. So just wanted to demonstrate that a little bit. This is the 14 bus model that we were talking about. All right, so I want to point out that if you're looking under electrical, it's the three-phase model that we're using. And all of these components that I'm going to just quickly drag and drop come out of that set. That the three-phase is essentially the distribution part of the modeling. So in this case, I'm going to zoom in on bus 14, and we'll drag and drop the transformer, the line, the bus. I just like to have a bus. And then the load. And right now it's a three-phase load, which is not very interesting as far as that goes. Let's see here. I can't see my, there we go. So I connect everything up. It goes from the transmission system to the transformer, and that's a single line. It includes all three phases. And then we extend out from the transformer as each A, B, and C phases. Now I'm curious, how many of you use System Modeler? Okay, so I'm showing you stuff maybe that you'll use in the future. And then the second question I have is, how many of you understand power systems? All right. So I would, some of these, the generator and the power systems are all kind of, if you have questions for them, please ask me, but I'll continue on this way. This is specific to the system, so we'll do it as quickly as we can, since there's not that many people that really do this. So we've got a full system. We've added a distribution system to the existing 14 bus transmission system, which is actually from 1962. It's a transmission model from American Electric Power, AEP, and it's got 14 buses and 5 generators. It's kind of like a standard way of people who do this type of thing would look at it. So let's switch to the simulation. You can see I've selected voltages in this case, which would be, if you're thinking of a water system, voltage is your pressure. And in the case of I didn't look at the currents, but they're similar. The reason I didn't is if I plotted on the same graph, then the scale is out. The currents are actual levels, and these are per unit. So when you see 1, that is your desired voltage level. It's normalized to 1. And in this case, we put a fault on the line, which is kind of like if you're in a electric power system and somebody were to take a 20-foot chain and throw it up over the top of all 3 phases, and it landed on those 3 phases all at the same time. That would be a fault. The system is protected for that, but it would short the current. In other words, what is flowing to the ground, which is I don't know. It's a little hard to explain, but with that said, this shorts the voltage to ground, and you see the dip then in the voltage, and it goes back up. So if what you would see in terms of lights is your lights would dim or go off. I hope I've explained that well enough, but all right. Is there anything else? I think that kind of covers that. I'm going to go back to the slides and kind of give the justification of how we validated the models, because I think that's an important part of this. So let me share. Yeah, so you could see in this model, it's not as prevalent because transmission systems don't really worry about the power factor as much as the angle of the voltage, right? So, but in the case of the distribution system, you can see the power factor, right? So it just depends what you're looking at the moment. All right, so. Okay. So I'm going to explain what it means to verify the model translation by describing the challenges, showing what it looks like when they're not the same, and showing the models that are the same. So you can separate most components within OpenIPSL into 3 types. Models from the Power System Analysis Toolbox, PSAT, by Professor Federico Milano's work. And if you're in the business, that's a pretty common thing to hear. Models from PSSE, the translation, and models that are original to what Luigi's worked on. Recently, I've attempted to simulate OpenIPSL test cases and examples in System Model. Most of the PSSE test cases work, and there are other non-PSSE components that work as well. So in generic terms, we created tests that were translated PSSE and SIM models and compared the results with each. And you can see on the left that they weren't following each other, and it's just regular regression testing. And those values are posted from PSSE. The actual program are posted in a GitHub repository, and you can find those. So this is the IEEE 14, and it compares not just PSSE, but the SIM results. And you can see they're almost identical. I think that's the best case for showing that it's validated. And then, so they've gone to the trouble of running it on different types of machines, Mac, Linux, Windows, with many different sizes of systems. So the New York system is a 500 bus system, which is pretty humongous in my terms anyway. And it runs, all of these run within maybe 150 seconds in the previous version. So we're going to get it back up to that as soon as we get more time. And you can see the number of equations that they had within each one. So I'm just going to kind of explain my part. Mostly up until about a month ago was translating the model itself, and that required work with another company that actually does the SIM translation out of PSSE, and it uses SIM from what's called CGMES, which is the European version of the standard to create the SIM. These types of exchanges are expected in Europe and not really expected in the United States, but will help Europeans as much as just a straight translation from PSSE. I take those SIM files. There are 5 different files that I used and converted them using an XSLT. Now, if you're familiar with Wolfram's use of XML, they already have a version. Actually, they suggest you use, instead of XSLT, just use their commands. So I'm going to try to translate that and put it straight into Wolfram. Let's see here. As far as the translation of the PSSE, they come up with two types of files, raw and DYR, and they wrote a Python script to do it all. It's pretty straightforward if you run Python. There is a way to port that into Mathematica, although it's just one additional step. So, all right. So I know I'm finished a little bit early. I'm hoping that we have more questions. I just want to essentially say that we've come up with a consistent simulation results between PSSE, SIM, and Modelica, and make this workflow viable for city utilities. I think we could easily start doing extensible simulations above and beyond what is possible in PSSE. And with the ability to add things such as FMI, vendor support, if you're familiar with those, they're essentially created in other tools and can be brought in. So things that are done in Simulink, such as solar or PV farms or something like that, could be brought in here and extended the model even further. So that type of thing. And the ability to look at both transmission and distribution is a compelling reason for us to use it. So I'd also like to go over some of my own system modeling of interests. System modeling uses essentially as a one-stop shop for system analysis in city utilities. And we provide, or I provided, strategies and principles for each engineer that was doing their design. And it helped to upgrade industrial parks and increase capacity at substations in ways that nobody else could do, because we were looking at overall system instead of being focused on just replacing that single transformer that's 47 years old. If you're familiar with the transformers, they should be used, or most vendors say you should replace them every 22 years. So when they're double that age, we not only think about what's present, but we look into the future and we decide, okay, where is our customer base going to grow the most? We can incorporate load models into it that are much easier to analyze using Mathematica. It just makes sense all the way around to do this type of modeling. And then, so customers generating and usage is what we're trying to match. As he described earlier today, they have to match because there really isn't much storage. They're trying to incorporate a lot of storage into the grid right now, but that's not come to fruition. So their power energy usage correlates to time, temperature, load type, and their redundancy requirements at a minimum. So how does that look on the transmission and distribution system? I keep repeating that question. That's a really important question for me. So the other thing is maintenance schedules are complex calculations involving rerouting power at precise times and certain weather conditions. So we have a limited workforce, and our ability to predict those times and actually see different ways. So having the ability to look at all parts of the model, not just what's coming in, but how we can switch it in optimized ways is important to me. So with that said, are there any questions? Sure. So I think it's a big question, because I see System Modeler as an extension of those pieces of software to begin with. And then Mathematica becomes, I have the desire to create workbooks that take test reports. So I get test reports back from the vendors related to the transformers that essentially create my models. So it'd be very nice to create workbooks or packlets of workbooks that take those reports and create the model from it, because it's a lot more complicated than just 4 variables to create a transmission line or create a transformer. There's a lot of testing that went into that to begin with. So, you know, that interface is important. Then related to simulating, the number of variables that you're allowed to have is just way beyond any of the other tools that I've used for modeling. And does that answer your question? I would say Modeler does the modeling, System Modeler does the modeling, and Wolfram does all the scripting and automating for me. I mean, that's where I would be hitting. The idea is correct. And I can say that, you know, as long as you can do it with their PSSE files, you can get the whole model. Right now, it's still transitioning to the sim. So yes, the speed to model creation is much better with this because of the translation. And then you're exactly right. You extend, it extends everything that PSSE does in order to more fully model your system with stuff that can't be provided by them. So, I mean, my first slide was probably the best example of stuff. So we had, I'll go back to that. It doesn't even matter. essentially things like whether to run or how much to run our natural gas system in combination with the electric system so that we know, do we need generation or are we trying to heat our customers? This happened all at the same time. It wasn't two separate events. So yeah, and so essentially it's so flexible and it's got to be really fast for us to do it.